Okay, welcome back for the afternoon session of the Automating Insight Teachers Conference. I hope you all enjoyed the morning session and a good lunch. So the idea of the afternoon speakers, so the first two speakers gave us kind of a broader introduction to so kind of like the philosophy of machine learning, kind of what it is, how it's kind of helping science in a bigger picture, and then we saw this one example of helping with electronic structure, and then Lauren went into great detail about how one of these machine learning models work, and I just thought I'd mention, I think Yasaman will mention as well, that that's really how these models, many of them do work that are like the state of the art. That same story with these weights and biases and neurons, that's not like a cartoon of the model. It's really kind of how they actually look, just with some extra layers or a few more neurons. So tying into that, our next speaker is Yasaman Bahri, and she currently works at Google, but has a physics background. She got her physics PhD from Berkeley a year or two ago, and then she did a residency at Google Brain, and now she's full-time research scientist at Google Brain. So it's a pleasure to have her, because she's going to be telling us more about the kind of state-of-the-art style of the kind of thing that Lauren told us about with neural networks. So, Yasaman.
Thank you, Miles, for the introduction. So I hope that through this talk I can give you a sense of what the frontiers of deep learning research are like. A lot of my emphasis will just be on deep learning. Lauren gave a very nice introduction to some of these ideas, but that means that you have some network where you send in some inputs, and you have very many hidden layers that are doing some computations, which just involve doing some matrix multiplications of your input, followed by application of nonlinearities. And you do this over some number of layers. That's the depth of the network. That's the deep in the deep learning part. And so I'd like to give you a taste of what research at this frontier is kind of like, then also talk a little bit about my own work, and then snippets of research that other people work on. So please do stop me and ask questions, because I'm not sure quite if I got the level of this talk right, so do slow me down if something isn't clear. Just kind of as a global view of different types of learning, Lauren talked about machine learning and AI. That's one distinction between two different fields. Another way to kind of classify some things that come up in this field are these three different kinds of learning. There are also some other types, which I haven't listed here, but broadly speaking, there are these three classes. One is supervised learning. So that's the kind that actually has had the most success in recent years with deep learning. And that's where the learning problem that you have consists of learning some functional relationship between inputs and outputs. So you have some training data that consists of inputs X and outputs Y. And there's some underlying functional relationship between the two, and you're just going to learn what that functional relationship is by looking at some finite number of samples. So that's what deep neural networks are really good at doing, and it's a problem it's an area we've made a lot of progress on. Unsupervised learning is when you don't have labels or answers for the actual problem. So let's say you just have inputs, you just have samples X, and you'd like to discover something about them. Maybe you'd like to understand the underlying structure that's there, but you don't really know what it is. One way you might do that is just try to plot some of your data and see if you can visually see some of that structure. But what makes this hard is that you don't know if the basis in which you took some of your measurements is actually the one in which you're going to observe the structure. So you kind of need to discover that. And this is a very open area. We haven't made as much progress on it. We don't really know what the right approach is. And then there's also reinforcement learning, which is more connected to things and ideas from control theory. But the setup there is usually that you have some agent that's interacting with the world. And because it's interacting with an environment, there's some uncertainty that's associated with that. So if the agent were in a perfectly closed system, and you knew what all the consequences would be of the agent taking actions in this environment, then the problem would be closer to control theory and would be easier to solve. But the agent here in this setting is interacting with some environment that you don't really know. And so the agent wants to, for instance, do something optimal. So as the agent kind of explores around in its space, it receives some rewards for different kinds of actions that it may take. And then the agent wants to learn what is kind of the optimal sequence of actions it should take to obtain the best rewards. And so solving that problem, basically because you don't know, you can only get some rewards by actually doing this exploration kind of strategy. You have to learn by exploring, and that's kind of the domain of reinforcement learning. And Lauren already touched on some of the differences between machine learning and AI. So machine learning is more just making machines that do intelligent things, tasks that can kind of aid humans, and often draws very closely, very much from statistics and computer science, but it's a little bit more domain limited. So you specify the domain, and then maybe you can just use pattern recognition, for instance, to kind of do something intelligent. It doesn't have to be very human-like. But then the goals of artificial intelligence are to build some more general system that can maybe do lots of different tasks. And for this, the field draws from, it's very interdisciplinary and draws from other areas like cognitive science, neuroscience, and so on. Okay, so why is deep learning so popular now? It turns out that some of the basic primitives for deep neural networks have been around since the 90s. So for instance, one of the main types of networks that is very good for image classification, so let's say you have a training set consisting of images of cats and dogs, and you have these samples, and then you want to learn this functional relationship. So one type of network that does that very well, and I'll try to come back to say a little bit about what this primitive is the convolutional neural network. And it was actually first introduced in the 90s by Yann LeCun, who was one of the pioneers of deep learning. And so at that time, people tested these methods, but they weren't really performing all that well or in a very impressive manner necessarily. And then all of a sudden, this current wave of deep learning started around 2011, 2012. And this was one of the papers that really brought it back. It introduced an architecture called AlexNet, but actually the architecture itself, so this way of basically taking inputs, doing certain linear algebra computations, so matrix multiplications, passing them through nonlinearities and so on through some number of layers, the sequential kind of processing from input to output. So this architecture, the primitives were really close to networks from the 90s, but nonetheless it resulted in very impressive performance. So this was kind of the breakthrough AlexNet result, and I took the abstract of the paper that had this breakthrough result just to give you a sense of the scale of the problem. So this is the network that was classifying 1.2 million images. The data set here is referred to as ImageNet. There are 1,000 different classes. The network is huge. It has 60 million parameters. It has 5 layers. So that means like each one of these application of nonlinearities counts as a layer. So depth 5. And then to make training faster, we used non-saturating neurons and a very efficient GPU implementation. And then it beat it was the top entry, beating the state of the art by about 10%. So one of the things that made this network perform really well, or the two things that are mentioned in this abstract, are just changing the type of nonlinearity you use in the network, and then also this access to a GPU implementation. So one of the things they did in this paper was historically people had used saturating activation functions for their nonlinearity. So if you think of a tanh function, it saturates at plus or minus infinity in its input. What they did was switch to using what's called a ReLU nonlinearity. So it's a hinge-like function. So in one direction it kills the input, it kills it to 0, and then in the other direction it's just a linear function. So just switching the nonlinearity resulted in a 6 times faster speedup of training. And then there were additional training speedups coming from the GPU implementation. And those two together, combined with the size of the data set and the scale of the network, are what kind of brought deep learning back into mainstream research. So that kind of highlights the elements of deep learning in the modern age, where modern here means since 2012-ish. It's very large scale. So these 3 things combined were kind of the beginnings of what helped relaunch deep learning. So access to large amounts of data, millions of images, for instance, very large models with many parameters that all of which need to be learned. So you're not sure what those parameters are. You've just defined an architecture at the beginning by hooking up these different, by defining when you write your program, as you saw with Lauren's tutorial, you define transformations in a certain way, but all of those transformations have parameters that you don't know. And that's learning means to fit those parameters. It's just some very complicated high-dimensional curve fitting that you're doing. So large models, large amounts of data, and more compute. And those three things together have already pushed us into a regime where previously there were tasks that weren't possible to solve. So I guess the point I'm making here is sometimes, even if you take an approach that is not very, necessarily doesn't seem very intelligent, when you push the scale, and you can achieve an impressive kind of performance. And then in particular, if you were to take some of these networks and have them now interact with one another in interesting ways, you could potentially have even more interesting results. So it's not clear that just because you have subsystems that on the surface look kind of boring, when you hook them up together and train the entire thing in the right way, that some of the structure of the task that you're trying to solve is actually is learned well, and you kind of the fact that you can solve the problem is kind of an emergent phenomenon, which is something that I will come back to.
Can I ask, the more compute, does it mean like more layers, computational layers?
So that's the more in the size of the models. So part of that is the depth, for sure. Part of that is also just the width. Sometimes you don't need to, so the depth is kind of like sequential processing. You might also want to increase parallel processing. So within a single layer, you have these like neurons, which are just the application of the nonlinearities. And you might increase the number of such parallel computations you do as well. So that's the size. But more compute here was actually just referring to access to like more GPUs and CPUs, so that you can train, and in particular to GPU compute, which is particularly good for this.
GPUs mean graphical users?
Yes, graphical processing units. Yeah. Okay. So once we were kind of pushed into that regime, then people could start to play around with some of these basic primitives to make them more interesting and rich. So this, I wasn't quite sure how much of it would be familiar to you, but here are some basic primitives. And I'll just at a very high level kind of want to say what those primitives might be. So one kind of, the primitive that you saw in the last tutorial involved just matrix multiplication and then application of nonlinearities in a pointwise manner. So to each like scalar computation that you did, you just applied a nonlinearity. These convolutional networks, which were the ones I referenced earlier, they kind of changed the structure of the problem. So now instead of doing one giant matrix multiplication, you'll do a small matrix multiplication with some filter. And that filter, as you move it around in your image, you produce some new modified image, some new map, which is kind of detecting potentially where you have signals of a particular kind as you move this filter around in your image. So I don't have either a mathematical form or an actual graphical form, but just like kind of at a very high level, you have a certain receptive field in your filter, and you kind of, to produce the output in the next layer, you just do some multiplication by moving this filter around across your image. And that's good for problems that have statistics that are have spatial translation invariance. So they're kind of homogeneous, at least at the statistical level, like images, for instance. Another primitive is pooling. So you collect a bunch of information, but now you need to aggregate it at the end of the day to produce some final, for instance, smaller dimensional output. And so, for instance, if you have an image, you want to aggregate information from all pixels in the image at the end to produce some decision. And that's what a pooling kind of primitive is. Recurrent structure is kind of what's shown here. So it's more for sequences, data that has a temporal nature to it rather than the spatial. And what recurrence here just means is that you use kind of the same computation at every time step, because the problem, again, has statistics that is time translationally invariant. It's about the same at every time step. So this is a complicated looking model, but kind of what you do is at each time step, which you can't really resolve, you send in some element of your sequence. So this is x at time t plus 1, and so on. And you do the same computation A here at every time step. So that's the recurrent structure. And here A, inside of it, can have more complicated details. It's really just a kind of a shorthand for more matrix multiplications and more nonlinearities that are inside of that thing. There are skip connections. That was a very important primitive structure that helped with networks where sometimes when you have a network that is very deep, the distance between your input and some computation you do at some layer that's very far away. So that distance grows and you lose information about the input. So sometimes you want to redirect some of the information from the input back into another layer that's deep in the network so that you can do some more processing with that. And then some of the bigger primitives, or primitives that have really helped solve more state-of-the-art problems, are things like attention and external memory. So attention kind of defines new coefficients, new parameters again. These are all things that need to be learned, which allow you to look at different parts of your, say, sequence or of your image, and to basically not just look back at one time step, but to be able to look back at many different time steps or many different places in an image. So kind of allows the system to decide where it wants to look by itself rather than you specifying that. Okay. I think in the interest of time, I won't talk about this bottom thing, but I will talk about this top thing, which is now that you have an architecture, and Lauren also touched upon this, how do you actually do the training? And right now we're in the era where we take the optimization-based approach. So we have some output. So this Z is the output of a neural network. It's just a function now, and I've specified it depends on all the parameters in your system, theta. So that's like I've aggregated all the entire collection of parameters into that single variable. So it's many-dimensional variable, and then x is the input. So for every x that you send in and for every choice of parameters that you have, you get some new output. For instance, it's the plus or minus 1 depending on whether you're thinking about a cat or a dog, for instance, as a class. Now, what you do is you just kind of very, in an unprincipled way, kind of just add a cost function to the end of this network, which penalizes you if the value of your produced by your neural network for the training set points that you have does not match the actual true values y sub I. So these z sub i's was just my shorthand for evaluating the function at point x sub I in your training set. So you have all these z sub i's, and you want to make sure that your neural network is learning those values on the training data set. And this is some cost function or loss function L, which depends on all of these parameters. This could be the millions of parameters in your neural network. And now you just want to minimize the cost. So it's an optimization problem, and you can run various descent methods like gradient descent or all sorts of variations on that. And that's the training part. And once you have some learned parameters in your problem, then you can compute the function value for all possible inputs that you care about and see how it does on new data that it hasn't seen before.
Can I ask you a question? Actually, so I noticed you wrote for instance, it could be the difference between the output you get and like the right one squared. But then of course it could be like the absolute value of that. It could be like a fourth power.
Yeah.
You know, like on the research front, are people coming up with theories about like why would squared be a reasonable choice versus a different choice? So, like how different those are?
It's definitely a research question. I don't think there are super clear, like general enough answers. I think it seems to be the case that if you use cross entropy for classification, that's quite good, and especially in combination with certain nonlinearities. But that hasn't exactly been sorted out either. I think probably once we understand the dynamics of networks themselves a little bit better, like it's mixed in with the choice of loss. Okay, so now I'll probably kind of segue into my own research before trying to give a little bit more of an overview of research across the entire field. But so I made the transition from theoretical physics to working on deep learning theory, or trying to understand how neural networks work. And I want to kind of highlight some of the major challenges that have been identified by the field, some of which are actually quite theoretical and fundamental. So this is like a description to give you a sense of, I tried to give a sense of maybe where the practical front is, or where engineering and empirical questions come in. Here's a sense of maybe theoretical questions that people are interested in studying. So this is a description from the Institute for Advanced Study special program on theoretical machine learning. And I just want to read it to you. So the design of algorithms and machines capable of intelligent comprehension and decision-making is one of the major scientific and technological challenges of this century. It is a challenge because it calls for new paradigms for mathematical reasoning, such as formalizing the meaning or information content of a piece of text or an image or scientific data. The algorithms involved must scale to very large input sizes. So these are like usual issues of scalability that come up in computer science. And then finally, because the obvious ways of formalizing many computational tasks in machine learning, which come from theoretical computer science, are provably intractable in a worst-case sense and thus calls for new modes of analysis. And in particular, this new modes of analysis, new paradigms, formalizing information content, I think for folks who are in theoretical physics, some of this is kind of close to the heart of what theoretical physics is about. But these are really like foundational questions, and that I just want to kind of emphasize that the field is, of course, much younger than physics, and so some of these foundational questions about how to even think about these problems is not very clear at the moment, or still being developed. So has machine learning become alchemy? This is like a provocative title I took from a talk by Ali Rahimi. It's a talk he gave for an award that he and Ben Recht won. It's at one of the major machine learning conferences, and I encourage you to check out the talk on YouTube, if only for its entertainment value. But also it has interesting points that come up here. So he kind of he took the opportunity to make his award talk about the state of machine learning at the moment, having spent a lot of time in it, many years in it. And so maybe some background context on this, and also this picture, which is great, as taken from his talk. The state of deep learning since like 2012 has been a lot of trial and error. There isn't a lot of principled ways of going about these things. So as you saw, there's so many there's a huge design space in terms of the architectures I can choose. And that's a really rich class that I kind of want to, may be really good for my problem, maybe enables me to solve harder problems in ML and AI. On the other hand, there's really no principled way to go about it, and sometimes what you find is that you strip complexity from the state-of-the-art problem, and you realize you don't need it. Other times you realize that the performance comes from tricks on top because the core approach is flawed. And so this just is overall to emphasize that now machine learning is kind of in a phase where it needs to move from alchemy, which has produced impressive results, to something that's a little bit more principled. It's a mixture of science and engineering, and it's not this. And to that note, I want to read this other description here, which kind of ties in with this new modes of analysis. There's a quote, this is taken from a short summary in Science magazine that was published in Science, if you want to check it out. But Ben Recht, a computer scientist at the University of California, Berkeley, and co-author of this keynote talk, says AI needs to borrow from physics, where researchers often shrink a problem down to a smaller toy problem. Physicists are amazing at devising simple experiments to root out explanations for phenomena, he says. And so I think this ties into the new modes of analysis need to not be worst-case analysis, they need to be appropriate for the problem. A key word that's kind of come up now in the field, people have rebranded this a little bit as science of deep learning. So let's try to understand what's actually happening in these complicated models and go about things in a principled way. Okay, so a little bit about myself, just quick, and I'm happy to talk more about this after the talk, but my educational trajectory. So I got my degrees in physics. My PhD was in theoretical condensed matter physics on the quantum many-body side. That's a field that I like very much. And so before I actually even really talk about the machine learning, I just want to talk about, make kind of a sales pitch also for quantum many-body physics. So I think that it's one of my takeaways from graduate school was that it's a very interesting way to think about building theories for systems that are very complicated and potentially have a lot of interactions. And in some ways, I kind of think that maybe that perspective I'm hoping could be useful for things like machine learning and AI. There are some key terms that I want to mention because I think one thing that one could do is expose high school students in physics to some of these more sophisticated but very rich and interesting ideas related to like many-body physics or the principles of emergence, which is like this idea that you may understand the microscopic behavior of the individual constituents in your system. But even if you do that, when you put them together and they're all interacting, some new interesting behavior emerges that's potentially seemingly complicated, but again, you need to build a theory that's appropriate for the problem at that level, which is, maybe needs a little bit of creativity and doesn't come, it is related to the microscopic physics, but is something that's a little bit different. So this idea of emergence and one of the kind of big philosophical, themes, which can be found in this paper by a very famous theoretical physicist, Phil Anderson, which I also encourage you to check out. It's an old article published in Science called More is Different. It talks about how that many-body physics perspective and ideas of emergence can be very useful for building theories for more complicated systems. So a little bit, this is one snapshot of a problem that I'm working on before I go on to other problems. But I mentioned at the beginning that now the trend in the field is towards overparameterization in these neural networks. And one of the big problems for theory is why do neural networks that are very large perform well? And this is counter to, say, your cartoon notion of low-dimensional statistics or low-dimensional curve fitting. So imagine, you're trying to fit some polynomial to your problem, and you see that your data actually falls on on a quadratic, but you try to fit it with a quartic. And you know that that's not a good fit for your problem. And so if you were to add more and more coefficients for higher degree mononomials to try to fit, you would get overfitting. Right? But and that's some of the theory that comes out of classical computer science, statistical learning theory, is kind of close to that idea, which is that you just add more parameters and you're more prone to overfitting. And somehow that cartoon picture isn't quite right for neural networks. What we're finding is that we add more parameters, and actually they not only perform well, they perform better than if you had made them smaller. So it's almost as if many of these parameters in a neural network are actually kind of pseudo-random. They're not actually being tuned that much, and maybe some of this residual randomness in the problem actually has some beneficial effects. So that's something that people want to kind of try to understand. It's counter to usual notions of overfitting that you might have in like lower dimensions. So one concrete case that we've been working on is trying to understand what happens to neural networks when you make them quite wide. So earlier I talked about there's this depth dimension, which is the number of sequential processing transformations the number of times you do sequential processing, and then there's also this parallel processing. So what if you took the size of this hidden layer to be infinite? Because we see empirically that the performance tends to increase when you do that. And if you study the problem in the infinite width limit, which is the kind of thing a physicist would do, take a limit, identify a limit that's interesting, take that limit, see if you can solve the problem or shed some light on what's going on, and then kind of perturb about that. And that's kind of been promising for us. We've been able to map these neural networks or make clear correspondence between neural networks in this limit and other objects from probability, if this is familiar to you, Gaussian processing. But these are like well-studied distributions or functions. And so trying to take something that seems complex, map it down to something that is better understood is one way to kind of make theoretical progress, which I think is very much in line with how physicists try to solve problems. Okay, so now about other kinds of research problems. One of them, which I think Lauren also touched on, is related to this optimization landscape of deep learning. So not a lot is known about what this landscape actually looks like. And that's part of the magic and the mystery. So historically, if you want to take the optimization-based approach, you might, because at the end of the day, you might want to have guarantees on how well you do. You might try to formulate your problem or even formulate your curve fitting problem in such a way so that you're guaranteed to have an easy optimization problem. So what does easy mean? It means like something like this, right? This is like a convex optimization problem. The cartoon picture is you just have a single bowl, and so if you were to initialize your again, collection of millions of parameters, imagine instead of this two-dimensional space, a million-dimensional space. You start somewhere up here, and you just roll down to the global minimum, which is the thing you want. So if you could formulate the problem in such a way so as to be guaranteed this, and historically this has been something that people have pushed for in the field, then that would be nice because you could have guarantees. You could have some sense of how well you're actually doing. But if your landscape looks like this, for instance, you have no idea what is the quality of these different minima. What if the one that has quite a lower cost is somewhere over here, but you get stuck over there? So this is a highly non-convex landscape. And at least when we take this approach where we just write down a very a parametric model which has very many parameters, kind of put together in a way that with no actual guarantees, then it's not clear what kind of problem we have. And this was one of the reasons that some people historically in the machine learning community didn't like deep learning, because it didn't have a guaranteed optimization problem. It was non-convex. One of the interesting things about this deep learning comeback is that by pushing things into this regime that we are now, where systems are much larger, they're at scale, we seem, at least to find in practice, that we can do the optimization reasonably well. And so maybe this picture is not quite right. One thing that's kind of hard is that our geometric intuition can be very misleading in high-dimensional spaces. So even that, some physicists or ideas that were taken from physics had a good impact, had a nice impact in the research community even in recent years. For instance, people thought that the optimization landscape of neural networks was plagued by local minima. But what people have now started to understand is actually the right kind of, in these high-dimensional spaces that would arise in neural networks, you're plagued by saddle points, not local minima. So saddle points are points where you actually have one direction of descent. So you're not going to get stuck. It's not as problematic if you were running some descent algorithm. And so this is an evolving story. So here are some example pictures, for instance, between two different kinds of architectures. The difference between these two architectures have to do with these skip connections that I talked about earlier, where you can take information from the input and send it to deeper layers. And what you find, for instance, or what this paper found, is that it has a smoothing effect on the loss landscape. So this is a better optimization problem because you just fall down, if you initialized here, you just fall down to the minimum than this one. And so you see that architecture plays a huge role in the optimization problem, and we're pretty much in the dark right now as to how all that zoo of architectures, what kinds of optimization problems do they correspond to. Any questions? Okay. So maybe also just a comment before I move on to the next part of the talk about older connections between physics and machine learning. So my focus has been on deep learning, but there's a very large branch of machine learning called probabilistic graphical models that took many ideas from a branch of physics called statistical mechanics, where people study the problem of many interacting classical random variables. And so in this sort of approach to machine learning, the type of thing that you would do is draw some graph. These are you can think of them as like classical spins, if you like, in a physics problem, if they were binary. And these connections in your graph kind of denote a kind of interaction, for instance, between these different variables. And so although it's evolved, this field has evolved a long ways from statistical mechanics. It has its early roots in many ideas taken from physics. And so that's one, I want to use that as one example where ideas from physics have made their way into machine learning. Okay. So here I just kind of want to give a flavor of it's a little bit biased flavor of the landscape, the research landscape of machine learning, and both talk about some successes, but also susceptibilities. All of these examples are outside of my area of expertise, but I still wanted to so I wouldn't be able to say much more than probably a slide or two about them, but I still wanted to put them because I think they give I'm trying to give an unbiased view of what's going on in the field at the moment, at least. Okay, so this part has to do a little bit more with architecture. So how can we make models for sequences? So earlier I talked about this recurrent structure. The recurrent structure meaning you would want to, if you have some problem, let's say a sequence where you know that the statistics of the problem is approximately invariant with respect to translations in time, then you might want to do the same computation, which is denoted A here at every time step. So what are you doing? You're sending in inputs. These could be like specific characters, X sub t. So you send in an A, you send in a B, you send in an X, and so on. If you're dealing with, say, language, and you get some outputs on this other side, and then these arrows in between these two boxes correspond to transferring information from this computation over here. And although this is all like very modular symbolic notation, again, I emphasize what's happening inside is just like linear algebra and application of nonlinearities. And these arrows really just mean you're passing some vector in maybe some high dimensional space from this computation over to the next computation. And if you were to look inside one of these A's here, this computation, you would see different ways that the input can be kind of forked into two pieces. You can do different kinds of, and apply different kinds of functions to them and then put them back together. So people have made quite a bit of improvement from just this vanilla recurrent structure over the past two decades ago. So one of those has been, for instance, to not just send, this arrow in between two different cells is referred to as the hidden state. You don't observe it, but it's something that passes information from one time step over to another. And people have added more kind of connections between these two different, cells at different time steps. This is an example taken. This is an example of an LSTM, where in addition to passing in the hidden state, you're passing in some cell state as well, which maybe is kind of like you can think of it as maybe a memory line, where there are some things that you want to remember, maybe for a different time scale than the things that you're passing in over here. And then depending on what you apply to that, for instance, you can apply nonlinearities, which kind of act like gates. They can allow information to pass through or not. And you can then have a little bit more ability to forget or retain information when you have this kind of richer architecture. It's also easier to train. So one of the challenges with sequences, which includes language, music, speech, is how to deal with long-range dependencies. That's exactly, by that I mean exactly what you would expect. If I want to say something, if I want to make a prediction, say for the next word at a certain time step, sometimes that comes from just local information. I can look a couple words back, but sometimes I need global context as well. I need to look back many sentences, and the system needs a way to kind of remember that information as well. And so long-range dependencies is still kind of an open challenge. Can we find better ways of dealing with that? One advancement has been the idea of attention. So rather than kind of force the system to pass information here from time step t to t+1, you kind of allow it to choose where it wants to look. So in the interest of time, I'm going to skip over this slide and show you a little bit of this one. So in this example, we have, this is an example from machine translation. So neural machine translation refers to using neural networks to do machine translation. But you have pairs of sequences from one language to another. So here at the bottom, you have English, for instance, and at the top here, you have French. And so when you pass in the sequence here, you allow all of these weights that connect, that maybe allow the computation done up here to refer back to computations done in this other source sentence at various points. And sometimes it looks in a very local way. So that maybe you have alignment between different words when you want to translate. But sometimes you might want to look over a couple words back, or maybe even very far back down in the sentence. And so this idea of attention has moved machine translation and language problems quite a ways forward. This is a visualization of these coefficients, this attention matrix, which is basically plotting the strength of these coefficients. It's telling you where, when you want to do translation to a new sentence, you're going to look back onto your source sentence.
So is the darkness, I see some lighter lines in there too, so is the darkness of the line like the size of the number?
Yeah, the strength of the connection. So that it's a kind of a probability distribution. I'm not sure what's plotted here. They're treated as like probability distributions.
I guess I can see that's the ordering of adjectives in French versus English, where you put adjectives before. Is that what that is?
You might be right. I actually don't know French.
I just noticed that. Yeah, it's the other word is real. Kind of cool.
Okay. I can tell you more offline about some of these. So there have been a lot of successes in language, but there are also a lot of susceptibilities. So examples of this include if you just introduce a little bit of noise to the system, so random errors, even human errors, the performance can drop quite drastically. Some of these systems are known to be susceptible to hallucinations. So you can just insert one token word into your source sentence and then completely change the outcome of the translated sentence. And of course, that's very different from how we think about sentences. So here's an example that a human would understand, even though it's been permuted around quite a bit. Right? I bet everybody in this room can understand what this sentence says. And so it points to the fact that maybe some of these networks are just memorizing. We do have a sense that that's kind of the case. On the other hand, they have had impressive results, and it's unclear how far you could actually go with just learning statistical correlations, or as I said at the beginning, if you took models that each learn statistical correlations, but you put them together in the right way, whether you could solve truly difficult tasks. And this idea is kind of referred to now as differentiable programming. So it means kind of just write down a program. What we're doing here is writing down programs, but in terms of mathematical computation. So like some linear algebra, some nonlinear functions. And so you're parameterizing some function, and what you really want to do is keep the entire thing differentiable so you can use gradient-based optimization, because we think that works really well. We still don't know why. But it's unclear how far we can actually get with this, and perhaps we can solve many more problems if we do this in a principled, intelligent way. So here's another snapshot. It's a different kind of approach to the one that I mentioned, where you try to have principled design of architectures. So given that there's this huge design space for architectures where you're kind of hand designing, a human is designing them and then training them and so on, can we just automate that procedure of learning itself? So let's have two neural networks here. One is kind of like a parent and one is a child. So there's a controller neural network that as its output suggests new architectures for you to try. And then a different part of your program takes that architecture as input, trains it on the problem that you care about, and then depending on how well that architecture did, you send a feedback signal into the parent to let it know what new suggestions it should make as to new architectures. That's kind of an idea of automated machine learning or meta learning, so having kind of a hierarchy of parent and child neural networks teaching each other what to do. There's a lot of work on generative models. So what does this mean? This is different from kind of a different idea than classification, when we were talking about taking inputs and just telling me, for instance, whether something is a cat or a dog. Here, what you're trying to do is, can I learn a model that gives me samples from a distribution that I care about? So what I'll send into the model is maybe just noise, but at the output of the model, I want to be able to get something that looks like it's drawn from the distribution that I care about. For instance, it could be the distribution of faces of celebrities or something like that. So that's the idea of a generative model. And one interesting idea that has taken root in the past few years is to take ideas from game theory to solve this problem. So in this particular example of a generative model, which is called a generative adversarial network, you have, again, these two neural networks. One is D, one is G. And to solve this problem of generation, you have them compete with each other. So G, the generator, that's the thing that in the end you're going to use. What you do with it is you send in noise, and it's going to produce samples X, say samples of images, samples of faces. And you would like this generator to actually be good, because you want to produce some fake samples from this underlying distribution that you want to be able to characterize. On the other hand, you have access to some real data. And so the discriminator here is something that is going to look at both of these, both the real samples and the fake ones. It's not going to know which came from which one, but its job is to try to distinguish the two and do that as well as it can. So the discriminator wins its game if it can distinguish between fake and real. And so this is kind of an adversary. The entire problem is phrased as something that you can differentiate end to end as a program where D and G compete with one another. So D's job is to tell you whether something is real and fake, and G's job is to produce something that is as good as the real thing. And this is a very interesting idea. It's pretty hard to train, but people have made astonishing progress on training these in different ways. For instance, they found these results are from something called progressive GAN, where they grow G and D in complexity as neural networks together. So part of what's hard about this training problem when you have something that's adversarial is that if one of them is from the get-go stronger than the other, then it tends to win and it doesn't give a chance for the other one to get better, to improve. So one way of trying to fix that is kind of having a more regulated environment where, for instance, how they solved it was having D and G grow in complexity together. But even for such systems right now, it's kind of unclear whether they're sampling from the true underlying distribution that you care about, or are they really just looking at so many samples that they're basically memorizing the training set. And then it also brings into play, well, what is the difference between memorization and learning? It's always some continuum between the two, right? So that's something that people are working on.
Although you asked about memorization, but are those images in the training set? Like, are those two that were in the training
No,
set?
these are new. These are new,
Ones?
yeah.
Like, so those, it just made those up.
Yeah, but then you would want to check, well, so I actually excluded the one that looks like a real celebrity. So sometimes you'll get something that might look like something that was in the training set. And you would have to like quantitatively kind of evaluate that, which is also hard.
Well, wait a minute, I know that guy.
You know this one? I don't know them. So how much time do I have?
Well, you're kind of into your question time now, but we still have some time for questions, so we should go to questions.
We should go to questions? Okay. My other examples were, in any case, about security and privacy. So there are ways to fool neural networks now that people have been trying to solve. So just adding a little bit of correlated noise that's not random but chosen in a very particular way can completely change the behavior of the neural network. Privacy is a huge issue. So it turns out that even there are ways to kind of invert. I won't say anything about how people actually do this, but you can kind of just query a model without having access to its parameters, and then try to maybe draw some conclusions about the actual training set or what was in the training set. And so a differential privacy is an entire area of theory that has grown around how to do this kind of in a robust way. There's interpretability also, which is trying to kind of get neural networks to explain how they reach a decision. So this is an example from actually one of the really nice success stories of deep learning in medicine, where for diabetic retinopathy, it's a project that was done at Google. And one of the things here, you can see that the problem was to identify these green areas are basically where the network looks when it wants to make draw some conclusion about blood pressure or make some predictions about that, and it's focusing on the blood vessels. But this is an example of a case that works. A lot of cases in practice for how to do attribution and interpretability don't work that well. There's also reinforcement learning, which would be a whole talk in itself, so I won't go into that, and I'll just leave that up there.
Talk. Okay, so we have still about 5 minutes or so for some questions, so please fire away.
So Google is supporting your research, right? Where do they see the outcome, and how are they going to capitalize on this? What's their profit, so to speak?
So the team that I'm on, so I should say a little bit about Google Brain. Brain is a team that does a lot of just pure deep learning AI research, and the goal of the team is really just to publish kind of as if you were kind of doing research in academia. So we publish openly, and I think the team, when you think about the size of the team in comparison to all the other projects that Google pursues, it's kind of small. I think that the idea is, for the research that I've described, is that it's good to invest in longer-term research, and at some point, even though you publish everything and the community is very open, so you open source code, open source the models, if something interesting comes out down the line, then of course Google could use it, but so could other companies as well. So it's pretty open, I would say, at this stage. There's a lot of research that's more applied, which uses proprietary data sets and things like that. And that's, of course, not as open. Yeah. I would say like the total investment is kind of small. And I think it can be kind of fruitful to have cutting-edge research done at the company. And also one additional thing is that research has very much shifted from academia to industry since 2012 because of this aspect of scale. So from a researcher's perspective, it's an exciting place to be because you could build systems that would be really hard to build if you were just a PI working by yourself in academia. And from a theoretical perspective, that makes it interesting for me to be there because if there are interesting empirical results to understand.
Okay, more questions?
I have a question.
Okay. Yeah.
The picture you showed of the picture you showed of the panda turning into the gibbon, and you said somebody has chosen some very careful noise to add to the picture to make that happen, right? Mm-hmm. Is that related to this overfitting of the parameters? As in, if you're in that regime, is it easier then to find such destructive signals?
That's a good question. So I think people, I don't know, only very recently people have tried to connect it, I think, to overfitting. But the connection to overparameterization in general is something that people have wondered about. Like, is this just a problem in a sufficiently high dimensional space? And I think that's kind of the thinking, but it's still kind of pretty open. And I should say that although that noise that I showed, it's not random, it's also not super hard to find. So you can find it by an easy optimization problem. So there are just very select directions that you can find with short amounts of optimization training, but you wouldn't get that if you sampled randomly.
Right. Thanks.
I'm just asking a question. A few years ago, Google, they had programs where, not want to say facial recognition, but giving a face you're able to detect. And it really had a problem detecting those who were of color.
Yes.
And my question is the bias part that's coming in because you're setting a set information in and you're feeding in data.
Yeah.
Has that changed? I mean, what has happened prior to that?
That's a huge research area also as well. I didn't put it on any of my slides, but that's something that people are definitely working on and taking seriously. They're trying to. I'm not familiar enough really with the approaches that they're taking, but there's an entire fairness team subset of brain that works on that. Unfortunately, I can't say much about the approaches because I'm not as familiar with it.
You mentioned how wider neural networks with more parallel processing perform better. So how would that relate to when you add noise, you have more local minimum? Would that interfere? Or how do you reconcile?
So you would guess that it would, of course, give rise to more local minima. Yeah, and naively, that's what people also thought, but it seems not to be the case. Actually, very recently, this is work that I talked about at the conference yesterday, but in this infinite width limit, we actually can kind of say that there's a certain regime that many networks access that is actually just convex. So effectively, there's one limit that we can solve exactly where the loss landscape is just bowl-like, at least when it's infinitely wide, and then we'd like to understand as you get away from that, how does that destroy this loss landscape? People have found that there's a certain regime from under to over parameterization where the landscape becomes more rugged, and they've kind of tried to relate that to systems in physics near a jamming transition and so on. So there is, as you make the network wider, there is kind of a critical regime where the landscape suddenly becomes rugged, but then it seems to transition into something smoother, at least as you make it wider. But these other dimensions of the problem and a richer class of models, people still don't really know much about.
Can you give us a sense of the scale when you say over-parameterization versus under-parameterization? So, are we talking about 10-to-1 parameters versus inputs, or talk about that.
That's a good question, and I don't have a good sense of that because both of them for me are in the order millions or billions when it comes to the larger scales. I think it's something that would be actually interesting to plot for a lot of the state-of-the-art networks, which to my knowledge, I don't think anybody has kind of gone through the literature and tried to characterize things that way. One thing is, well, like it's not, that kind of counting of parameters against the training set size comes from a linear model way of thinking. And it's not clear exactly that is exactly it. People have been using it and it seems to be useful, but it's not exactly clear that for a nonlinear problem, the right measure of over or under parameterization is just to compare number of parameters to the number of constraints. But unfortunately, I don't have really a good sense exactly where things lie.
I had a question actually, which is, are there some perspectives specifically from the fact that you have a background in physics that you are bringing or are planning to soon bring into the machine learning research you're doing now?
So yes and no, I think. Like loosely, I'm inspired by like the way that one would build theory in theoretical physics. But one thing that I don't want to do unless it's very natural for the problem is to directly import something that exists in theoretical physics and map it onto some machine learning problem without. I think the right way is to first like look empirically at what people care about in machine learning and what things are performing well and you think might have interesting underlying phenomena. Then decomplexify the system using approximations that are good for that setting. And then if it maps over to something in physics, for instance, that's great. But if it doesn't, then I also don't want to likewise be constrained by just physics models. I think it would be really exciting if we could kind of find new types of phenomena. I'm always on the lookout for places where connections could be made.
Okay, time for one more quick question, then we should take the break. Okay, any more pressing questions? And okay, if not, let's thank Yasaman again, and we have a 30-minute break. Okay, when we come back, we'll hear about quantum mechanics and about astronomy to wrap up the day. So look forward to that.